Okay, good morning, everybody. This is the Maprg session. I had a little problem sharing with my other brother, so I'm now on Safari and sharing my whole screen, which means I cannot really see the controls. However, I will quickly run through my sets of the slides. And then, if possible, I would like to ask the first presenter, Emmeline, to maybe share the slides on your own, or at least try that. And then I can try to fix that while we listen to that presentation. So that would be good. Welcome to ITF 109. We are online again. Nevertheless, we have some nice presentations today. This is the note well part about the intellectual property rights. Similar as the IETF, the IRTF has adopted rules about participation in intellectual property rights. And you should study those RFCs, which are linked here on the slide if you haven't seen this before, in order to know what you get yourself in when you're participating here on the mic or in any way, in the Jabber or anyway. We also have in the ITF a couple of policies about privacy and code of conduct. So if you want to participate here and you're not aware of these RFCs, please also have a look at them. And then the next slide is quickly giving you a reminder or some understanding that the IRTF is actually not the same as the IETF, what the difference are, how these two organizations work together or interwove. And there's another RFC you can study if you want to. This is the usual slide, which is more useful if you actually go to the material. So you can click on these links, find all the links you need. You find our charter. So what is this group about? You find the slides, you find the Meet Echo link, which you probably have found already, hopefully. And there's also the Jabber room. And this is our agenda today. So we have this very quick overview here because we have a packed agenda. We only requested 1 hour slot because this is an online meeting. And some people are in not the perfect time zone. So we try to keep this a little bit short, but actually kind of fortunately, unfortunately, however you want to take it, we got like a lot of nice contributions. So what we have today is that we have 2 longer talks. The first one about network fingerprinting and the second one about obligate DOE measurements, which are kind of brand new material. And then we have like the later 3s are only 5-minute heads up talks. Because these have been a really good piece of work, all 3 of them. But these have been published in papers in the IMC conference, and there have been presentations about that, and also the long videos about these presentations are available online. So if you want to know more, you can watch them, or maybe you've watched them in advance already because you're all prepared. And you can read the papers. All the links for the papers and the videos are in the agenda. So if you look up in the data tracker, click on the agenda, you get more information there. And with that, I will try to stop sharing here and see if Emmeline is available to maybe share herself.
Yes,
that would be great.
Should I share my screen?
If you can, that would be great for me.
Okay, so I'm clicking, where should I? It's the first time I'm using this tool, so I don't know how to share my screen.
So yeah, next to the video and audio button, there's also the screen sharing symbol, basically. So if you can click that one, and I can grant you that. Let's see.
Okay. Yes, that's me. And these are my slides.
Okay, perfect. Thank you.
Okay. Hello everyone, and thank you for listening to this presentation on network fingerprinting and routers under attack. So first, I will introduce what motivated this work with Archer research questions. Then I will talk about fingerprinting, what it is and how it works. And after that, I will review our methodology for the experiments that we did. And finally, I will comment on some key results that we found. Okay, so for our first research question, here we are interested in knowing what is the hardware ecosystem within the internet and within operators. So here, actually, we want to discover where the different brands of hardware, that is to say, Juniper, Cisco, Alcatel, etc., where those different brands of hardware are located inside the network, and what is the role that they play. And knowing this is actually important for a second research question, which is what could happen if an attacker is able to identify the brand of a router and use that information to launch a targeted attack on said routers. So from the output that we get from question 1, we can get a view of what could happen in such a scenario. And these questions are motivated by the fact that recently there are 5 vulnerabilities that have been found in Cisco devices, vulnerabilities that can lead to remote code execution and denial of service attacks. But there's not only Cisco, there are also several other manufacturers for which a vulnerability in the RSM implementation has been found. So first, a bit of background. How can we actually tell the brand of a router? Well, this is called fingerprinting. And the basic idea is to send some probes to a device and analyze its responses. So recently, there was a very lightweight fingerprinting technique that was proposed, and that relies only on 2 different probes to be able to get the hardware of the router and sometimes even the operating system. And so this technique is based on a specific field in the IP packet, which is the time to live field. So routers, when they send a packet, they put an initial value in this field, which is almost always 30, 32, 64, 128, or 255. And so the people who have found this technique have also shown that it is enough to get these 2 values for a time-exceeded packet and an echo reply packet. So these 2 values, we call that the router signature. This is what tells us what is the brand of the router. And in this table, you can find the different classes of hardware that we are able to identify with this technique. We can differentiate between Cisco, Juniper with the operating system Junos E, and the last class, which is composed of Brocade, Alcatel, and Linux machines, and that we will call the BAL class. Okay, so on to the data we collected. We use TNT, which is Paris Traceroute extension that comes with this lightweight fingerprinting technique that we just talked about. And additionally, it can also reveal MPLS tunnels. So it has the potential to discover more IP addresses than the classic traceroute does. And we launched TNT between the 1st of November to the 13th of November of last year, over 28 vantage points, and overall we collected 1.2 million addresses. So from these traces, we then used another tool, MIDAR, to perform alias resolution, which is the process of identifying which IP addresses belong to the same router. And so from the IP level topology that we got with TNT, we can get a router level topology with MIDAR. And this is actually interesting for us because these topologies, they are closer to reality, they are more concrete. And so we can better study network resiliency and robustness on this kind of topology. So with our tool MIDAR, we were able to identify 65,000 routers, having altogether 200,000 addresses. And finally, the last bit of processing that we did on the data was to use the tool Border Mapit, which allows us to determine who is the owner of a router. In the sense, what is the autonomous system that operates this router. And our goal here is to delimit as precisely as possible the different ASs in the network to study hardware ecosystem at a finer scale. Okay, so back to our first research question. What did we find? What did we find? Well, let's first look at the internet as a whole. On your left here, you have a graph that gives the signature repartition for both addresses and routers. And what we can get from this graph, basically, is that Cisco largely dominates the overall market. So we can see, for example, that nearly 60% of the routing devices are actually Cisco devices. Now, if we look at a finer scale, at the scale of the autonomous system, well, this graph gives us, once again, the hardware repartition, but for 4 large ASs this time, for AS A, B, C, and D. And what we can already see from this graph is that the hardware repartition can be very different from one AS to the other. For example, with ASA, we see a lot of Cisco devices, but for ASD, it's not the case at all. We see only almost Junos. For ASB, we see also a lot of Junos. And for ASC, we have a nearly equal mix of BAL and Junos routers. So yes, what we can conclude here is that different ASs have very different hardware ecosystems, and it can also be very different from the global point of view. Okay, now on to the second research question. Now that we know more about the AS's infrastructure, what could happen if an attacker is able to easily identify the brand of a router and then use that information to launch a targeted attack? Well, the first thing to know here is that not all routers contribute equally to forwarding packets in the network. Okay, we have small routers, we have big routers with a lot of forwarding power. And so if it turns out that a certain brand of router is important for forwarding the traffic, and if that brand of router has a vulnerability, then it could be a target of interest for attackers to target those routers. So how are we going to measure the impact of an attack on a brand of routers? Well, we already saw the hardware distribution that I've put back here. So for example, if we look at ASA, we could say, okay, we see a lot of Cisco routers, so we can conclude that Cisco routers are important for forwarding the traffic. But actually, the amount of routers does not necessarily reflect the amount of traffic that is being carried. So this is a first indicator, yes, but we need another metric to measure that. And this metric is the hardware popularity. We compute the hardware popularity as the proportion of traces that cross each brand of hardware. And this metric, it has been shown that it reflects the actual amount of traffic. So what do we get when we compute it? Well, here it is. We see that actually it's quite close to the hardware distribution. So our first indicator was already a good one, but still we can see some differences. For example, for ASC, in terms of number of routers, we saw a nearly equal mix between BAL and Junos. But when we look at the amount of traffic that is being carried, we see that actually BAL is more important for forwarding the traffic. Okay, so how did we proceed with our experiment? Well, for each brand of router, we simulated an attack by taking down different fractions of the different brands of routers. And we looked at the impact in terms of traces impacted in the network. And we performed the simulation 30 times and averaged the results that you can see here on your right. So we have one graph per AS. Let's look, for example, at ASA. We can see here that it is enough to take down 20% of the Cisco routers to impact already nearly 60% of the traces, of all the traces in this network. So it's quite an impact already. And on the other hand, we see that attacks on Junos and on BAL routers, they don't have much of an impact compared to attacks on Cisco. So yes, this autonomous system, ASA, is quite vulnerable to attacks on Cisco. For ASB, however, this is not the case at all. Here we see that attacks on Junos are actually more harmful to the network than attacks on Cisco. So as expected, given the hardware popularity, we can see that not all ASs will react in the same way to different attacks. Okay, so time to wrap things up. What can we conclude from this presentation? Well, the first thing is that someone can very easily retrieve the brand of a router by sending only 2 probes to this router. The second thing is that the different ASCs, they can have very different hardware repartition and hardware popularity. And third, because of this, different ASCs will be more or less vulnerable to different types of attacks, depending on their hardware infrastructure. And that's it for me. I hope you enjoyed the talk. Thank you.
Thank you very much for this nice talk. And also, as you went through in time, we actually have some time for questions. So if people would like to join the queue, you have an opportunity right now. Yep, there's Brian. Please unmute yourself.
Okay, so they've changed it slightly since the last time. Hi. A quick question on the takeaways here. Would another way to phrase this be there are definite advantages to being a multi-vendor AS in terms of your ability to, like, so this basically is looking at the amount of traffic that's going through these architectures. Could this tool be used to quantify for a given AS what their return is on having, routers from multiple vendors, right? Like, so you could use this to map yourself as opposed to what you've done is to map it from externally.
Yes, it's actually, well, in the paper we have a few suggestions for network operators, and one of the suggestions we didn't put, but I think about later, was that maybe there could be an advantage for autonomous system to have several vendors, several manufacturers, in order to not be that vulnerable, to not rely on only one single brand. But maybe a drawback of this would be in terms of management overhead. Maybe it's complicated to deal with that many routers because there are different.
Cool, but there's like actual data on the vulnerability side of that from this paper, so that's cool. Thanks.
You're welcome.
Thank you, and that also reminded me that Brian nicely volunteered to take notes, so thank you for that. Any other questions? Okay, then thank you again. We move on to the next talk. And we have Sadish online here, and he will also try to share. I should be able to grant that. And it's coming. Nice. Okay.
Am I audible?
Yes, you are. You can start. Thank you.
Okay. Yeah. Thank you so much. So, hello everyone. Thank you for being here today. I'm Sadish, and I'll be presenting the measurements of a privacy-enhancing DNS protocol called ODO, or Oblivious DNS over HTTPS. And this work is the result of a collaborative effort between lots of incredible people at Cloudflare, and was a part of my internship this summer with them. And this talk will focus on the ODO standard proposal that was co-authored by Apple and Cloudflare, and we're committed to actually moving this forward. As a quick introduction, DNS is the domain name system and is the foundation for the human usable internet. It responds to client queries for host names with the corresponding IP addresses and records. And traditionally, the DNS protocol is not encrypted, and it uses UDP, which continues to be a majority of the traffic received by the public recursive resolver, which Cloudflare operates. And the usage of non-encrypted DNS leaks user information to network operators, to on-path adversaries who are observing the network, and even allows active attackers to modify the network request from the client or the response from the server. But to overcome some of these problems, there have been recent efforts to secure DNS using DNS over TLS, DOT, or DNS over HTTPS with DOH. And these have been gaining popularity and have been integrated into various web browsers, operating systems, protecting the client traffic from being observed by onlookers or being intercepted and changed by the attackers. But however, the resolver operator can continue to associate the client request to the IP address and build a profile around their browsing patterns. But over the past few years, we've seen active measurement research trying to understand and measure the impacts of encrypted protocols like DOE or DOT. And many large-scale measurements have shown that the performance of these encrypted protocols vary by the choice of the resolver, and it does not significantly impact page load times, and it improves user security. So there have also been various attempts to improve page loads using prefetching. But while DOE did improve the security of DNS queries for clients, it also received a lot of criticism because of the small number of publicly available resolver services, essentially centralizing the internet and giving these organizations a lot of control. But additionally, these resolver operators also can associate client queries with the client IP addresses and use the IPs to geolocate the client. To maintain privacy guarantees, some operators actively purge data exceeding 24 hours and give their users privacy policy-based guarantees. And bringing together a lot of organizations to agree to a common set of privacy practices is extremely difficult, and it requires explicit negotiation and a lot of effort. Mozilla, for example, actively defined criteria around data retention, aggregation, and frequent audits for the DOE services to be configured as a default to the Firefox browser. And while some users might be comfortable with this idea of having a policy-driven approach, these are difficult to enforce, and they're also very time-consuming, making users want a system that can technologically guarantee their privacy. And in this talk, I'll focus on the privacy critiques and the ability for the resolvers to be able to create a profile for their clients. And this is exactly where oblivious DNS or over HTTPS or ODO kicks in. At a high level, there are three main components in ODO. The first are the clients who prepare a query for which they would like a response. And the goals of the clients in ODO is to be able to successfully send encrypted messages, receive valid responses to decrypt, and in the process, be able to identify if there are any malicious actors and take any corrective actions. The second is a proxy instance whose main role is to relay the encrypted queries and responses to and from the targets while removing the client IP addresses. And the third is a target instance, which receives the encrypted query from the client, decrypts it, obtains the DNS response for the query, processes it to retrieve to get a response, encrypts the response, and sends it back to the proxy. And it has no ability to identify who the actual client is by the IP address. But at a high level, the design of ODO is similar to that of DOE and injects an intermediate proxy node, which terminates the client query over here, Q, and performs the query on the client's behalf. And the main goal of ODO is actually to prevent recursive resolvers and ISPs running such resolvers from being able to link the clients to their requests. So a client encrypts their query using a hybrid public key encryption scheme and using a validated public key from the target resolver and sends this query to a proxy instance. And there are various ways in which the clients can actually learn about these services and validate them through DNSSEC. Look for conflicting keys. But however, in this talk, I'll be punting on this problem, but there are more details that are available in the report. But in ODO, the proxy instance can see the IP address of the client, but not the contents of the DNS query, and forwards this message to the oblivious target, which decrypts the query and obtains the response from the resolver. And the response is encrypted by the oblivious target and is sent back to the resolver, who sends this message back to the client, where it can be decrypted. And in this process, the target only sees the DNS content and not the actual client's IP address. But we often say the target resolver as like independent entities, but this need not really be true. Ideally, in practice, for performance reasons, the oblivious target and the recursive resolver could be co-located, and this avoids the additional network messages between the oblivious target and the resolver. But it is still possible to maintain these as individual services without any co-location. But now with the understanding of the protocol in place, we actually set out to understand and measure three main research questions. The first one was, what is the impact of Odo on the DNS response times? And how does this protocol affect page load times and user experiences? Also, how does this compare itself to other privacy enhancing protocol techniques that are actually out there today? And this helped us understand the cost of privacy while maintaining the security guarantees and the need for performance. This slide pretty much sums up the results of our measurement and is probably the most interest to all of you. But I'll leave this here as a reference to come back to just in case anyone wants to refer to the slides. And in the next few slides, actually talk about the measurement that we perform and detail each one of these takeaways. So let's get to the measurement. We implement and deploy the oblivious targets and proxies using Google Cloud and a serverless platform like Cloudflare Workers. And we physically separate the oblivious target instances from the resolvers and randomize the query from the targets to three public resolvers, to Cloudflare DNS, Google DNS, and Quad9, which we use in our measurements. We use 9 Google data center locations, 7 across the United States, 1 in Montreal, Canada, and 1 in Sao Paulo in Brazil, with 10 client instances running at each of these vantage points, performing the experiment of sending DNS requests at a rate of 15 requests per minute, which is the average number of DNS queries sent by client devices with high internet usage. And the average bandwidth that we have for all the clients running on a single core Intel Xeon is roughly 480 megabits per second. But the clients perform DNS response time measurements by choosing pairs of available proxies and targets. And by choosing a low latency proxy target pair for the measurement, shown in the orange line here, we find that the average query response time improves by 22.8% compared to only choosing a low latency proxy, as shown in the green line. And this hints towards the fact that having an intermediate proxy on the same network path to the target will improve the response time performance. And this path, however, can be quite different from the path that a UDP-based DNS packet might actually travel on. But what about connection reuse? And connection reuse is an optimization that can enable clients to improve their performance by at least 46% on an average, and it avoids unnecessary TCP and TLS handshakes for each request. In our experimental setup, we evaluate for the worst case performance and incur an additional network latency between the target instance and the resolver in the architecture that we showed before. And as we see here, the target instances, which are located in Google Cloud and performing queries to 3 open resolvers, have faster response time for Google DNS because of potential co-location within the same data center compared to the other services. And integrating the oblivious target into the recursive resolver can reduce the network latency incurred to that of a cache hit for the answer. And in the cache miss cases, incurring the network cost for the recursive resolver to communicate with the other name servers. So we find that co-locating these services does actually result in better performance. But to understand the performance of Odo, we compare these to other protocols offering similar privacy and security guarantees and use DO as the baseline protocol, which is shown here on the indigo line to the left. And the DO over Tor is a variant of DO which provides both security and privacy guarantees in addition to some anonymity guarantees. And this is the beige line that you see to the right of the figure. But when we compare this to Odo, we notice Odo with no service co-location achieves an interesting position roughly in between DO and DO over Tor. And these results get interesting and better as we start to co-locate the target and the resolver together, which is shown by the dashed blue line over here. And we notice that the response time for Odo compared to DO for the baseline increases by 50% with service co-location and 100% when the target and the resolver are not co-located. But DNS protocols with message encryption like DNS Crypt or anonymous DNS crypt tend to have much larger compute overheads and use non-encrypted channels. And these protocols have higher response time and lie somewhere in between Odo and Do over Tor, which is over here in this region on the graph. And the performance of these response times with Odo somewhere being in the middle ground is very interesting. Is very interesting for us. But this brings us to a crucial measurement that we're really interested in: the page load time impact. And to do this, we establish a measurement node in a lab network with an available on-path and a randomly chosen off-path proxy. And the node runs a local stub resolver, which is configured to use Do and Odo protocols for various runs. And in each run, we browse the same set of pages after purging all the local cache entries and perform page load time measurements with Selenium while using the navigation events. Our first measurements presented here are pessimistic and use the worst case network architecture with no service co-location, and only considers the complete page load time events instead of other metrics like time to first byte or the first useful paint. So additionally, there are a lot of various browser artifacts like caching, which happens within the browser, and this is the reason why the top graph over here is quite different from the stress test measurements and the results from the stress test measurements that we've shown before. But what we find in our preliminary measurements is that using Odo with an on-path proxy increases the page load time by 20% compared to a baseline UDP-based DNS usage or DO, and a randomly chosen off-path proxy actually increases this by 25%. So the page load times move from somewhere between 1.319 seconds on an average to 1.6 seconds with Odo. These results are still preliminary, and we're optimistic that with service co-location, these will get better, but this is still ongoing work. And to conclude, Odo is a practical privacy-enhancing protocol for DNS, and it has minimal page load time impacts, and the performance impacts of the protocol are purely like network topology effects. We make a lot of recommendations in our report for the ideal usage in production systems, like having an ecosystem of on-path proxies, having service co-location, and being able to and making the clients do connection reuse. All of the code and our implementation is open source and is available at these links on GitHub under the Cloudflare organization. And we're committed to move this standard forward in the IETF and hope that more operators join us in providing support for the protocol, either by running the proxies or the targets. And the report indicating our measurements is also available at this link here. Thank you. I'm open to questions.
Thank you very much. So this is, oh, we already have a queue. So this is kind of brand new results, right? There's no paper yet, but you're working on one. So as soon as that becomes available, maybe you can also share it on the mailing list. And with that, we take a first question from Mike. I think you have to unmute. Yeah, yes, sir. There you go.
Thank you. So I was just wondering, does the work that you have here support ECS or EDNS client subnet? Because it seems like the optimization that you're doing is really great for DNS performance, but on the other side of that, authoritative name servers may be being used to try and do geolocation-based load balancing, for actual delivery performance enhancement. And if that information is obscured, what's the balance? Have you looked into that at all yet?
So we haven't actually performed a lot of measurements for that, but to the DNS resolver, the proxy is essentially what they would see as the client. So any EDNS optimizations that are applied for, say, a proxy in a specific geolocation would continue to be applied. It probably becomes possible for the client to choose a proxy that is maybe at a completely different geolocation, and that might have some effect on EDNS, but we haven't actively measured them.
Okay, and Mike, you have another point? No. Then we have Brian.
Hi, Satish. This is really cool work. Thanks a lot for sharing it. Actually, your answer there is sort of a lead into my next question. So you're saying that you didn't really look at the the ability of, or the impact of actively choosing a proxy. You can actively choose a proxy either to maximize the confusion, right? Like to minimize the identifiability, or also to minimize latency. What I'm seeing in these graphs, though, is that those two tend to look like they're related to each other. You can either maximize confusability, or you can minimize latency, because the minimum latency path is going to point kind of in the direction that you're pointing in. So,
right.
I'm kind of wondering, I actually would like to see the follow-up work here sort of dig into that particular question, like what is the actual latency cost of additional, bits of confusion about who you are, because it looks to me like this basically takes the problem that Do was originally intended to solve, which is encrypt the thing to a gigantic DNS aggregator, which will obscure who you are. And because there's a need to obscure who you are from the gigantic DNS aggregator, we're now going to use smaller DNS aggregators in the proxies. They will obscure who you are from the giant one, but the giant one can still kind of guess at least geography based on the fact that everyone's going to implement for lowest latency possible, right? Because I mean, there's the impact of this over DNS over 53, you said, is up to 20%, which is actually kind of massive, and that's just latency table. So I guess that's more of a, please dig into that. In the future, I want to see sort of a curve between, hey, here's the x-axis of how confused I want to be, and here's the y-axis of how much I have to pay for that. Because if that curve can be pushed down, then you can make a really good argument that, okay, you should do this anyway. You're going to take the hit, but it's worth it. But if that curve is too high, then
So I think it's not only location; it's also linkability, right?
Right. So you're fixing the linkability problem, but I mean, if you're in a situation where only 3 people are behind a certain proxy, then you need to get the mass, and you're kind of flipping the mass argument that Do was intended to solve in the first place back around. So comparing other architectural variants.
Yeah, I think that's definitely like a very, very valid suggestion. But as Jonathan, I think, pointed out in the chat along with he said that it's not an either or in most cases. Like, you don't have to choose between one of them. There are probably ways in which we could scale them, but it needs like this close collaboration by a lot of operators and network operators to put some of these proxies on path and see how we can do this. But of course, one of the things that we noticed is that there are quite a lot of people who do use DNS script, which is over here as this gray line that you see. But the performance of Odo is like much better than DNS script, even in its worst case setting. So
cool. All right. Thank you very much.
Yeah. Thank you.
Thanks. We still have time. We're really good in time. That's really nice. I'm not used to that, but we don't have anybody in the queue anymore. So thank you very much for your presentation. You can ask more questions in the chat, everybody else. We will move on to the next presentation. And next we have Sebastian talking about DNS again. Are you able to share?
Working on that. Oof. Okay, my screen is somewhere else. There we go.
Yeah, we can see your slide. We can hear you. You're all set.
Yeah, apologies for the flickering. I didn't notice that before. Hello, everybody. Nice to be here. I only have 5 minutes, and this is an accepted IMC 2020 paper. So there is a longish version of this, a presentation, a video recording, so you can go and make a reference to that. This is a joint work between SIDN, the Dutch domain registry, the New Zealand domain registry, a root server operator. We joined forces to go and find out how the clouds are centralizing DNS traffic. So as you may know, and I have plenty of slides to go and justify this point, there are concerns from the US and the European Union about centralization of platforms and centralization of internet infrastructure. So there are hearings about antitrust, and you've heard, well, Facebook in there being a social media company or Twitter having too much power, about how are they creating a single point of failure, a point where they decide what is good, what is bad, undermining privacy of users, and also market consolidation. So our intent with this work is if we can do anything to go and measure internet centralization. And you can pick any metric you may want on this, the number of users, the amount of traffic, network infrastructure, as Emeline presented a little bit a few minutes ago, computing infrastructure, market power, market share. But because all of our three DNS organizations, we focus on DNS traffic. That's mainly coming from resolvers to authoritative servers. So, and we provide you with three different vantage points. So we have using passive DNS, so packet captures. We have the DNS traffic going to .nl, the Netherlands, with official language Dutch, New Zealand, English, Maori, and sign language, and Beirut. And we focus our efforts on measuring from 5 different cloud and content providers. So Google, Amazon, Microsoft, Facebook, and Cloudflare. 2 of those, Cloudflare and Google, as you know, and as you heard from the previous presentation, they have public DNS. So we would expect to see a lot of traffic from them. We did a lot of the aggregations, a lot of analysis. You can go and take a look at the paper, but what we can find and what I can quickly share here is, for example, how using different weeks of data in different years, the traffic has been growing. So you can see for Beirut, the traffic coming from those 5 cloud providers basically double in a matter of a year, and stay the same in 2020. However, the root servers and the CCTL and the TLD space are completely different beats. And you can see if, for New Zealand, almost a third of the traffic comes from those 5 cloud providers, which for the Netherlands is even worse. And you can see if I go back and forth, that the amount of traffic the Netherlands gets from Google is around 15% of the total load. We can focus on different aspects, but basically we can see from IPv4 and IPv6 options, and at the end of the slides I have a beautiful picture that shows Google and Cloudflare basically share the traffic between IPv4 and IPv6. That Facebook is starting sending more and more IPv6 traffic, and the Microsoft and Amazon barely use IPv6 as transport. If we focus on DNS by different query types, you can see the patterns and the footprint of each of the cloud providers are completely different. And you can see on Google specifically in 2020 how the amount of traffic they send for the NS queries drastically changed. The reason for that, and I have a pretty picture here, is basically because Google deployed QName minimization in December 2019, which leads us to part of our conclusions that if a cloud provider decides to go and adopt certain technology, IETF technology, you will see a massive change, either DNSSEC, UDP versus TCP, etc. So there are pros and cons of centralization. And again, I'll invite you to go and check the video presentation on IMC, RIPE, or DNS.org, or read the paper.
Okay, thanks a lot. Also, very interesting talk about a important topic we're discussing. We are still good in time, so we still have time for questions here.
Great. So, well, George is pointing out Q&A minimization is sort of a counterexample of where market concentration is a good thing to have. And I'm pretty sure there are other options. So Google also does DNSSEC validation. And because the Netherlands has a lot of DNSSEC domain names, it's likely an explanation for why they're receiving so much traffic. Cloudflare also does DNSSEC validation. So if the ITF comes up with a new technology or a new DNS query type that might be very useful for users, this market concentration will be very helpful for them. I don't see a lot of hands for questions.
No, I'm still waiting
Yeah.
a little moment because we, as I said, have time. I also recommend everybody to read the full paper. Really good paper.
Yeah, so if we have more time, I can show you one more thing, which surprises us. So most of the traffic received by the Netherlands and New Zealand is UDP traffic, except for Facebook. So Facebook has a non-negligible amount of TCP traffic. And by checking the EDNS buffer size, we notice they're using a very small buffer size. So they're likely querying for something, and then they have to go and retry on TCP the same query late.
Yes, so maybe something to discuss on the Maprg mailing list. There might be people from Facebook. But other than that,
yes, definitely.
Thank you very much for your presentation. And with that, I think we move on. Next, we have Oliver. And I believe you should be all set to start sharing. Yes, there you are.
All right.
We can see you. We can hear you typing.
Perfect. Can you see my screen?
Now it's up. Yes. Thank you.
Oh, awesome. Okay, perfect. So hi everyone. My name is Oliver Gasser. I'm a postdoc researcher at the Max Planck Institute for Informatics in Germany. And today I'm going to present a short excerpt from our study on the so-called lockdown effect, namely the implications of the COVID-19 pandemic on internet traffic. So as you all know, right around March, a large part of the overall population of the world went into so-called lockdown, which means that people were now working from home, they were studying from home and teaching from home, and also parts of the social life moved online. And in all of these efforts, the internet is obviously essential. And so we asked ourselves, how well does the internet actually cope with this kind of change? And we looked at a lot of data, namely a large European ISP, and 3 internet exchange points, one located in Central Europe, one in Southern Europe, and one at the US East Coast, and also at an academic network, Rede Madrid, which is a university network in Spain. And to analyze all of these data, we assembled quite a large group of people from different research institutions as well as companies. So let's get right started. The first analysis that I want to present to you is how does the traffic actually change during the lockdown. What you see in this graph on the x-axis, you see the calendar week all the way back from January 2019 to June 2020. And you see a horizontal line where you have the year change from 2019 to 2020, as well as some specific dates noted, for example, the COVID-19 outbreak, as well as the initial responses and lockdowns. And on the y-axis, you basically see the normalized traffic volume, which means that whenever the line goes up, traffic increases, and whenever the line goes down, traffic decreases. And the blue line in this graph shows the traffic volume for the ISP. And what you see there is that right around the initial responses and lockdowns, you see about 30% increase in traffic, which would normally span over multiple months within just a short period of time. If we now look at the internet exchange points in gray, we see a quite similar behavior there. And for some of the IXPs, the traffic level remains elevated even after some of the lockdown restrictions have been lifted. Now looking at a different network again, which is the mobile operator network in orange, which behaves completely different compared to the other networks that we've already seen. Namely, during the lockdown, the traffic goes actually down, which makes sense when you think about it, because people were more staying at home and not moving outside anymore. So they didn't use the mobile network as much as before. And also, once some of the lockdown restrictions were lifted right around at the end of April, mobile traffic starts to pick up again. So now that we've looked at the overall traffic volume characteristics over several months, let's look at a more detailed picture, namely, how does traffic change within a day? And for this, we're going to look at a working day as well as a weekend day. And so we picked a working day, which is February 19th, before the pandemic, before the lockdowns. And what you see on the x-axis is basically the hour of the day, and the y-axis again, the traffic volume. And we see how is the traffic volume distributed over the day. And what we see before the lockdown is that on working days, there is a strong increase in traffic towards the evening hours. If we compare this to a weekend day, we see that the traffic is more equally distributed over the complete day. Now, if we compare this to a working day during the lockdown, we see that the traffic more resembles a working day compared to a weekend day. So work days actually start to look more like weekends from a traffic characteristic. And finally, the last analysis that I want to show you is we also looked at different applications, how traffic for different applications changed. And one important applications when you're working from home is VPN. So we applied a port-based as well as a domain-based technique to identify VPN traffic. And in this left part of the graph, you see on the upper part of the graph, you see the traffic volume for work days. So again, if the bar is higher, you have more traffic, more VPN traffic there. And on the lower part, you see the traffic volume for weekends. This is the traffic, the VPN traffic for February. If we now compare this with March, we see that there is about a 200% increase in VPN traffic, mostly during the working days, in working hours. If we look a little bit more further in time, so at April and June, we see that the VPN traffic starts to slightly decrease again, but it's still, the volume is still above the initial volume that we've seen in February. So what are our main takeaways from this paper? We saw that traffic increased between 15 and 30% within just a few days. The difference between the work days and weekends starts to vanish. And also specific applications for remote work, such as VPN and video conferencing, saw quite a large increase in traffic. There is a lot more in the paper which we've presented at IMC 2020. For example, we look at changes in transport ports, different traffic classes. We also investigate how does traffic in an educational network change during the pandemic when students are staying off the campus and at home. And we also compare hypergiants versus non-hypergiants and much more. That was it from my side. Happy to take any questions.
Yeah, thank you very much. We do have like 1 or 2 minutes for questions. I also wanted to mention, I forgot this earlier, that this is like only maybe not fully in scope for Maprg, but we thought given the current circumstances, this might be interesting. It's a very comprehensive paper with a lot of different measurements. And there are also more papers at IMC at the Internet Measurement Conference. So if you look up the agenda from the last IMC conference, which was just like a few weeks ago, you find more interesting papers about these kind of effects. Let's see, we have people in the queue. So Jonathan.
Did you look at how weekend traffic changed? Did weekends just look the same, or have weekends become even more flat?
So weekends, you're talking about weekends?
Yeah, because you said that normal traffic looks more like weekends. Well, what does weekend traffic look like?
So weekend traffic still looks like weekend traffic, more or less. So it's the main thing that changes is the working day traffic. So I can maybe show us a backup slide, which I have here. And what you see here is basically we're trying to classify from the traffic characteristics whether a day looks more like a weekend or it looks more like a working day. And on the lower part, you see the days classified as working days. On the upper part, you see days classified as weekends, and all of the blue bars are classified correctly. So here, for example, we have weekends classified correctly. Here we have working days classified correctly. And what you see is that the weekends remain classified correctly. So they're still behaving like weekends.
Okay, thank you. We have
Thank you.
one quick question from Spencer.
Thank you for bringing this work to us here. I'm one of the editors of a document in the MOPS working group and operations about media streaming, guidance for operators, and this is going to be a great resource for us. Thank you.
Sure, thank you.
Thank you, Oliver. And with that, we go for the last talk. We only have 3 minutes, but maybe we can go 1 or 2 minutes over. We have Marcus, and let's see if you can share. Yes, there you go.
Okay.
Yes, we can see your screen. We can't see the slides yet.
Yeah,
we can see and hear you.
I try. So now you should be able to see.
Yes, perfect.
Okay. Okay. Yeah. Hi, everybody. I'm Marcus from RWTH Aachen University, and I would like to summarize our results of the analysis of the security configuration of internet-facing OPCOA deployments. So OPCOA is one of the most recent industrial communication protocols, which was designed with security in mind, making it a prime candidate for communication in the Industry 4.0 and the Industrial Internet of Things, for example, to control productions via the internet. And indeed, the security features of OPCOA are approved, for example, by the Federal Office for Information Security in Germany. However, to actually achieve this level of security, which is promised by OPCOA, extensive configuration is required. And to guide operators through this extensive configuration process, the OPC Foundation published official security configuration recommendations. However, the question still persists whether internet-facing OPCOA deployments are configured securely. And you might ask why this is relevant for the IETF, as OPCOA is no IETF protocol, but we think that this might be only a key example for secure by design protocols in general. So let's get into it. So first we have to find OPCOA deployments on the internet. So we performed active internet measurements weekly over a period of 7 months using ZMAP on the standard OPCOA port, and subsequently retrieved security configurations and publicly available payload data. And indeed, we found industry deployments using the OPCOA protocol. Between 1,700 and 2,000 of these deployments were reachable over the internet in the IPv4 address space. And 42% of them are discovery servers, which means that they are only used to announce OPCOA deployments on other IP port combinations. And we focused on the non-discovery servers here, as the security configuration is only relevant for the actual payload transmission. Then we answered the question whether these are configured securely. Looking into the security configurations of these deployments, first looking into the security mode, which basically enables or disables communication security features, for example, confidentiality and or authenticity. And here 1 out of 3 modes completely disables the communication security. And we found that 1/4 of all deployments actually use this one mode, basically neglecting all of the OPCOA security benefits and do not offering communication security at all. And furthermore, We looked into the security policies, which define security primitives to be used to implement these selected security features. And here, 3 out of 6 policies are not considerable as not secure, and 2 of them, because 2 of them are deprecated due to the usage of SHA-1. And we found that despite these were deprecated in 2017, 1/4 of all deployments that offer security still use these deprecated policies. And more interestingly, we found that only 1.4% of the servers we found enforce the usage of secure policies, which were recommended by the OPC Foundation. We also looked into whether the deployments implemented the security policies correctly by looking into the certificates the servers use for authentication, and found that 30% of the servers use 2-week certificates, which do not meet the minimum requirements of the security policies, for example, key length or hash algorithm that was used to generate those certificates. And furthermore, we detected several cases of certificate reuse, and one was most striking, as one certificate was deployed on more than 380 devices, which we think are operated by different operators, which we derived from the discussion with the manufacturer. Looking into the third aspect of the security concept, we also looked into authentication and found that 44% of the deployments do not implement access control, meaning that everybody on the internet can access these servers without authenticating itself. And we also looked into the payload data of these deployments and found that these are actual production systems as of our judgment. So our results underpin that deploying a secure by design protocol is not sufficient, but it requires, of course, secure configuration. And we think that also standardization could somehow help for that. For example, by specifying that implementations have to ship with secure by default configuration. Yeah, our paper is available on arXiv, and we also published our dataset in our scanner. So thank you very much for your attention.
Thank you, Marcus. Sorry that you now were a little bit time squeezed here. But also I recommend really to read the paper. I think even though this is not an IETF protocol, it's a really good example about what can go wrong. I think like you ended up with over 90% of deployed systems that have like some kind of a security flaw. Even so recommendations exist. So I think this is a good lesson learned read. So people should read the paper and look at this, and we should consider this in future. We can maybe take one quick question. We're already over time, but if there's something urgent, I would grant it. Otherwise, people can move to the list, ask further questions to Marcus, read the paper, or contact him directly. Thank you very much. And with that, we're at the end of our session. Thank you very much to all the speakers. I really enjoyed it. I was really happy that we got so many good presentations and talks. Thank you for everybody who participated, for all the questions, and then see you on the list or next time. Enjoy the rest of the IETF meeting. Goodbye.